Right. So, chapter is electromagnetic induction, and this will be the basis for slowly as we go for alternating current also. Okay, the chapter is electromagnetic induction. And in short, people call it as EMI, electromagnetic induction. Main ideas of this chapter. The main ideas of this chapter is number one, you can write down that is an induced EMF, okay? Induced EMF. Now, when I talk about induced EMF, so let me just give a brief uh, understanding out here because this is what we will be using throughout. Okay, now let's say so far you know that if you have a cell can produce what is known as a EMF, which is denoted by E, which is the electromotive force. When we say the word induced EMF, induced is something like cell will not produce now. Okay, the perfect example to this is you keep hearing a song for more than 5-6 times. Then when you are free, you start singing that song on your own when you have been doing something. So that song has got induced upon you. So here when we say the word induced EMF, we will be using the word called induced EMF. Throughout the chapter, we will be basically referring to one coil. And in this coil, an EMF will be induced. No battery or no additional EMF source will be connected to it. So it starts generating EMF. Have you understood? So there will be two words we will be using a lot. One is called an induced EMF, and another word we will say is induced current. Induced current. Now, what is an induced current? If the same coil which gets an EMF induced in it, have you understood? You have given some sort of what you call life to it. If you connect this to a circuit, let's say this is a circuit where we have a load, then it can allow the passage of a current in this circuit, and such a current is known as a induced current. An induced EMF is an EMF which is generated from within a coil or a conductor. Coil will be the word we will use more. Conductor is something we will mention, but whenever we are mentioning conductor, we are actually trying to talk about coil. Understood? So this coil will get an induced EMF. An EMF will be generated in this coil, and such an EMF is called induced. And it will be induced by some external property, right? It will be induced by some external property or external changes. What are all those changes? What are all those magic? Is all this chapter is all about. Okay, so you'll have an induced EMF. So whenever I'm using the word EMF, please understand that it's an open circuit condition, and whenever I'm saying the word current, that means that EMF generated coil has been connected to some external circuit. Understood? So the key ideas is an induced EMF is generated in a conductor or say a coil when the magnetic field, we are coming from level 0 definitions. Okay, this is just an idea. When the magnetic field linked with the conductor changes. This is a very high level definition of what we are going to say. So we have a coil, right? And it's all about an induced EMF is generated. So we will have a coil, right? Let's say we have a conductor. This is the idea of the chapter. This is a coil. This coil will get a induced EMF, okay? An EMF generated if the magnetic field linked with the coil is changing. Means this coil is right now kept in my room, so it is sensing, say, the Earth's magnetic field. If the magnetic field changes, this coil will develop an EMF in it. This is the broad idea of the chapter. Okay. Further, we will study that a changing, not exactly field, then we will see that a changing magnetic flux, creates an induced EMF, and you can say induced current in a closed circuit. Induced current in a closed circuit. All things we will be studying dates back to something around 1830. Persons responsible for it are Michael Faraday. Michael Faraday. So you will be learning about Faraday's law of electromagnetic induction and Joseph Henry. Joseph Henry. But these are not inventions, beta. These are discoveries. These are discoveries, but both these discoveries are independent. None is related to one another, whereas more of attributions are with Michael Faraday. So a changing magnetic flux can create an induced EMF, and that induced EMF can actually make an induced current run in a closed circuit. And the idea about this chapter is to learn about this induced EMF which gets generated in a conductor or coil when the magnetic field link with the coil changes. So you will learn about a new term called magnetic flux. You already have an idea about electric flux. So we'll learn about something called magnetic flux also. Shall we go ahead? Okay. Now, again in the idea part, go back to Ørsted's experiment. So what did Ørsted's experiment tell you? Ørsted's experiment told you that electric current gives rise to magnetic field. Didn't we study this? Right. And here comes the person, Faraday, Michael Faraday, who is now questioning whether the reverse is true or not. Can the magnetic field create electric current? Job becomes very easy. Once we get electric current, a lot of things will be here. So his answer was yes, with one condition. That this magnetic field should always be a changing magnetic field. It cannot be something which is static. So now have your idea. If you want to see, if you generate induced EMF, one good thing happens is that you can now have a powered circuit. But in order to do that, you need a magnetic field, but only a magnetic field will not do. The magnetic field should be changing. And this is what we will study in 3 experiments now. It cannot be stagnant. It can't be stagnant at all. With this, we start our chapter with 3 types of experiments. Okay. So a little bit of drawing. So let's go to our first experiment. Our first experiment is, so we have a coil here. Okay. Various turns of the coil. All right. And say this coil is connected to an external galvanometer. We have connected this coil to a galvanometer, right? And just to give you an impression of the coil. आइए सर. अरे कोई बात नहीं. Thank you, sir. So this is my coil, and let's say this is an axis, right? And on this axis, the first experiment will involve a magnet. So let me bring my magnet out here. Such that this is the north pole of the magnet and this is the south pole of the magnet. Fine. And now what we do, we will be drawing our magnetic field lines. So they originate from the north and end at the south. So your magnetic field lines will be somewhat like this. Right. You can draw this. This is my coil. This is experiment 1. This is experiment 1. Once done, let me know, right? You've understood, right? Simple coil, two ends of the coil are connected. Why did I connect to a galvanometer? To sense whether any current gets developed in this or not. And the broad idea that you have is that if you disturb the magnetic field that is linked with the coil, then definitely a current should be induced. Okay. At stationary position, as you are drawing, just keep listening. This coil is sensing the Earth's magnetic field, and a magnet has been kept out here. So it is sensing this field also. So total field that it is sensing is the vector sum of the Earth's magnetic field and the magnet's magnetic field. Okay? We done? Right. Point number 1. Write down point number 1. Magnet moves towards the coil. Magnet moves towards coil. Tell me, children, if you move the magnet towards the coil, aren't you not changing the magnetic field of this? Earlier you were sensing some X, now you will sense more than X, right? Magnet move towards the coil. Our finding is G deflects. Galvanometer deflects. Right? Very easy. Number 2. Magnet is stationary. Magnet is stationary. G shows no deflection. G shows no deflection. Third, now what did you do? Look here. The first operation was deflection. The second is the third will be magnet pulled away. Magnet pulled away. G will show what, beta? Opposite deflection. G shows an opposite deflection. And fourth, one more experiment was made. Magnet moves faster. In this we found G shows more deflection. So here actually two motions are hidden. Magnet either moving faster or pulled out faster. G is showing more deflection. Are these simple things understood? What was the first one, Zoe? Then truck, then truck, then truck. 4 things we've done. Okay. G deflects. What is your conclusion? Induced current is set up. Achha, why did I not use the word EMF here? Because I am connected in a closed circuit. So induced current is set up. No deflection, no current. Here again, opposite. So induced current in opposite direction is set up. And what does the fourth one tell you? Larger current, large current is set up. Pretty easy for us to understand. If you have more deflection, your current is large. Based on this, we are now in a position to make a conclusion of our first experiment. So children, write down the conclusion. Fourth one is faster moving. Move fast, withdraw fast. More deflection. The galvanometer shows more deflection. That is what we will study. That is what we will study. As I'm glad you asked that question, but keep that as a what you call suspense right now. So conclusion is, what is the conclusion you think? Can you give me a conclusion here?
It's dependent on strength of magnetic.
Well, you don't know anything about strength of magnetic field as of now. See, observe the experiment properly. That explanation does not answer this. Speed is one property. Speed is, once you saw current, you are now trying to test how to vary. The main thing is, once there is a relative motion between coil and magnet, that is the thing. Did you see one thing? Whenever the magnet is stationary, there is no current. Whenever the magnet moves, magnetic field and all is the idea of the chapter. See, the idea of the chapter is after studying the whole chapter. I gave you an idea. Actually, I should have started teaching you from here. The idea makes you understand what you are going to study. So from this experiment, we say, you can write down that current is produced only when there is a relative motion. Slowly you will find that the motion is not the thing that is responsible. Only when there is a relative motion between magnet and coil. See children, we will better up our conclusions. First conclusion is very crude. You just found if there is a relative motion. Have you understood? What does this mean? This also means that had you kept the magnet stationary and moved the coil, then also you would have seen a induced EMF. What is relative motion? I move towards you is a relative motion. You move away from me is also a relative motion. Have you understood? This tells you ये करने से भी होगा, इसको करने से भी होगा. But both cannot be in a relative motion of zero with each other. Done, children? Shall we go to experiment number 2 now? Okay. Let's go to experiment number 2. Experiment number 2, we again have a coil. Now we will have 2 coils. Experiment 1 was only with coil and magnet. Experiment 2, we have got now 2 coils. Once you have drawn, let me know. Done? So you can write in experiment 2, Faraday used another coil C2, another coil C2, and C2 was connected with a battery. C2 was connected to a battery. Now, why he did not use this magnet? Just see, C2 connected to a battery. A battery has a current that is flowing through a coil. Current carrying coil behaves like a magnet. Now I'll move this coil towards it. So a magnet, that was permanent magnet that we was doing. This is man-made magnet, right? So the experiment A is C2 moves towards C1. C2 moves towards C1. Our observations are galvanometer deflects. Galvanometer deflects. All right. And when moved away from C1, galvanometer deflects in opposite direction. Obviously, I don't expect any difference because instead of a magnet, I'm creating a human-made magnet. B and C, when C2 is still, you have no deflection in G. There is no deflection in G, right? So time for us to again make a conclusion. And if you want, you can write down that when you're moving C2 towards C1, induced current is set up. C2 moved away from C1, then also induced current is set up. So we can write here, induced current is set up. Here also, induced current in opposite direction is set up. And in the third, we can write no current. No current. So conclusion, you can write. Now we will better it. First, we did what better? We did relative motion between a magnet and a conductor. Do you agree? Now you remove the magnet. You created a coil which is carrying current. Do you have a relative motion now? Yes, we still have a relative motion. Can we better our first word? In our first word, we said relative motion between a magnet and a coil. It's not magnet. Relative motion between a magnetic field and a coil. Because you have to create a magnetic field here, whether you create it by a permanent magnet or you create it by a coil which is carrying current. So please write down a moving magnetic field. A moving magnetic field, and in bracket you can write not necessarily a magnet. Not necessarily a magnet can induce current. Can induce current. And here we find the relative motion is responsible. Relative motion is responsible. Which means between a coil and a magnetic field, you have to create a relative motion. So either the magnetic field moves whether towards or away, or the coil moves towards the magnetic field or away. You can always have a what is called a induced current that can be set up. Is this much done? Time for us to go to the third experiment, and probably one of the most important experiment. Can I swap? No? So we go to our third experiment. Again, third is same as first. Just same as first. In coil C2 circuit, put one key. So this is my C1. C1, and then my access, and I have important means not by syllabus, for most from the finding perspective. Let's make it. Acha, first time what did you find, beta? You found that relative motion is necessary. Do you agree? How did you do that relative motion? You found that the relative motion was created by a magnet being moved or pulled away, or vice versa, coil being moved towards the magnet. Then in the next experiment, what did you do? You abolished the magnet and you said it's not about a magnet. You need a magnetic field which should have a relative motion with respect to a coil, or a coil which should have a relative motion to a magnetic field. Now the third one is, and you still were adamant upon one term saying that relative motion is responsible. Now what we are doing, now we are making C1 and C2 both are stationary. Now we'll see whether the relative motion is needed or not. C1 and C2 are both stationary. Okay. While you have C1 connected to galvanometer, I have C2 that is connected to battery, that is connected with battery, as well as key. Key is done for what, beta? Key is done for switching on the circuit or switching off. Right. So let's see our observations now, and if we made them point wise so that, okay. A, number one, key is pressed. Key is pressed means, have you understood? You have just turned on the circuit. Key is pressed, then you find momentary deflection. Key is pressed, you get a momentary deflection. Your second is key is steady. Achha, what do you mean by key is steady? If you are on, you are in on position. If you are off, you are in off position. Either position, steady. Steady means you have understood? No disturbing. So here we find no deflection. No deflection. And the third one is key is released. Key is released. Released means you have turned off the circuit. You again get momentary opposite deflection. You will get a momentary opposite deflection. write down this much, then we will go for our understanding. Did you understand three things? Means is like this. See, this experiments we do actually lab. Switch on, tuck, deflection. On, no deflection. Switch off again, tuck, deflection. Off, no deflection. ठीक है? Write down. Okay, let's see what happened in the first thing. When you turn the switch, key is pressed. What about your current? Your current changes from 0 to maximum. Don't you agree? For few moments. The current does not become constant in one go. You switch it on, the current changes from 0 to maximum. When the current changes from 0 to max, your B, that is the magnetic field, changes. Clear? Later, B becomes constant. As the current has become steady, the magnetic field has also become steady. And when it is 0, B, when the key is steady, B is constant. B is constant. And when you do this thing, then the current goes from maximum to 0 for few moments. Again here, B changes. See, B changes. B changes in opposite direction. Opposite direction means whatever was a steady B, it comes back to a reduction. The B is changing in opposite direction. So I can write B changes, you see a deflection, so current induced. B constant, no deflection, no current induced. And B changes in opposite direction, again I'll write current induced, but in opposite direction. Now children, tell me, do you need a magnet? Go by experiment 1. Your job is to get a current in this induced EMF in this coil. Do you need a magnet? No, I can do it with a coil also. Do you need a coil also? Means I need a magnet with a relative motion. Okay, magnet gone. I need a coil with a relative motion, right? Third one, you had the coil but you did not have relative motion. What did the key do? The key helped you in changing the magnetic field, either less to maximum or maximum to less. If I abolish this part, and I introduce some mechanism by which the magnetic field keeps on changing here, do you expect an induced EMF here? Yes. हमें magnet से कोई लेना देना नहीं. Relative motion, that was one way. Now rather you think, then sir, why did you give that relative motion? Cross question yourself. The relative motion changed the magnetic field. Bringing a magnet and then moving also changed the magnetic field. Keeping the coil stationary and switching it off and on, by I was earlier feeling some sort of magnetic field, he suddenly switched on. He switches off, I can do this. Are you getting it? That means there should be some harkat here that you get a harkat out here. Therefore, we'll study later on mutual induction also, where you keep doing some activity here and you'll see some activity out here. Right? So now the time has come to write your conclusion. Write down. You can write down your conclusion. Relative motion is not essential. Relative motion, this is interesting chapter, is not essential. What is essential is a changing magnetic field. So you're right. A change in magnetic, a change, I'll use a new word now. A change in magnetic flux. You don't know what is magnetic flux, you just gulp it now. A change in magnetic flux with the coil is important. But sir, why did you bring this word? We were all talking about magnetic field so far. Somewhere I have to have a chicken and an egg issue. So is that issue? We will solve it in our next section. Don't worry. You need to change magnetic flux. You remember what was electric flux? Electric field lines associated with the surface. Are bhai, if you are moving and you are changing the magnetic field, aren't you changing the magnetic field lines associated with it? Okay, magnetic field lines are something which are imaginary. I am sensing a magnetic field. There are lots of curves going through me. Do you agree? The magnetic field through me changes. The lines change. And when lines change to a surface, lines per unit surface is flux. And when lines change per surface, flux changes. That's right. But we will explain what is magnetic flux. You remember electric field and a conductor gives you electric flux. So just write down this one. And though we will study Faraday's law, can I change the screen? Though we will study Faraday's law separately, but this is the basic on which Faraday's law is set up. Faraday's law. Faraday's law means they say Faraday's law of electromagnetic induction. I won't define the law right now. I would not do anything. It says that the induced EMF E is equal to negative d phi b by dt. Please understand. What is this negative? This also we'll study a little bit later from Lenz's law. Negative means, listen, what is negative all about? Person who gave birth to the child, our sir used to explain like that, the child will just do the opposite thing to the person right on birth. Means kill the person. What change brought you, you will just oppose that change only. Therefore, this EMF will oppose the very change. What was the change? You moved the magnet towards it. Say suppose you created the magnet by moving it towards it. It will create a force in which the magnet will feel repulsion. Are you getting it? You created this by increasing the current. Then it will create some sort of a back in which it will reduce the current. All this we'll study. And this comes from Lenz's law. For now, just absorb that the negative means, negative, you just write one thing. Negative is attributed to Lenz's law. We won't study it today. Lenz's law of induced EMF. And broadly it says this induced EMF opposes the very change that produced it. The way you brought me, I will just oppose that change only. The very way. Okay? Phi B is known as my magnetic flux. Magnetic flux, just like phi E was electric flux. So just see, what did you write in your previous statement? Just see, a change in magnetic flux. So what is change? Change in any quantities. D by dt means what? Change with respect to time. So you're doing d by dt means d by dt of phi B means change in magnetic flux with respect to time. So if you can do a change in magnetic flux with respect to time, you generate an EMF, and that's what is Faraday's law, which we will study. But this is what is going to come up. E is equal to negative d phi by dt. Okay? All this is understood for only one coil. So our time now to get into something which is known as the magnetic flux. Let us understand what is magnetic flux. And very easy examples. We won't define anything. We'll just see some examples. Magnetic flux. Write down, electric current is not produced by a magnetic field. Electric current is not produced electric current is not produced by a magnetic field, but by a change in but by a change in magnetic flux through the coil. You are not doing it by magnetic field, but in broad sense, magnetic flux tells you how much magnetic lines of force or magnetic field line passes through a surface. What do you mean by magnetic flux? It just says how many magnetic field lines pass through a surface. The surface can be that of a coil or can be a loop. You can have a coil or you can have a loop, and you're interested to find out how many magnetic field lines will be actually crossing through it. Okay. Some of the examples which are very easy to understand is, some of the examples are arrows passing through a window. Arrows passing through a window. Got it? The window is your surface. The arrows are the magnetic field lines. So how to understand this? These are some easy examples. We can take this as these arrows are your, say, magnetic field lines, and the window is your, say, the coil surface. Now you tell me like this. So if the arrows are more, if more arrows pass, it clearly means that more is the flux. Clear? And in the similar way, if we find that less number of arrows are passing, if this is less, then it means less is the magnetic flux. Have you understood this? Right? And if you feel that, sir, this experiment, this example confuses me, I'm not so clear with it, you can still have another example. And that example is more interesting. Let's say it's a nice rainy day and rains are falling. There's rain, falling rain. Right? This is falling rain. This is falling rain. Now, how do I do it? Yes. Say the falling rain is allowed to fall on a surface where my surface is held perpendicular to the falling rain. Don't you think lots of rain will fall? Right? And on my other one, what I am doing, I have the same surface like this. Okay, I have the same surface like this, but I've slightly tilted my surface. Got it? So this experiment is like, this is rain and this is perpendicular surface. So what do you get here? More rain. More rain is captured. So this is your analogy of more flux. Flux, see, this is uniform rain, means uniform magnetic field. Surface is also uniform, but you can vary the flux depending upon the orientation. Got it? The same rain and same surface, but tilted. Now you capture less rain. This is your analogy for phi b less phi b, and this is more phi b. I hope you have understood now. How much of magnetic field lines are related to a surface? The magnetic field can be constant in both cases. It depends upon how you are holding your surface. Okay? So shall we go now mathematically? Very easy. Mathematically, magnetic flux, same like electric field. Magnetic flux is a quantity phi b, which is given as the vector product of B dot A. Vector product of B dot A. Yeah. You be very careful in the terms of A, where A is beta what? A is the surface area. A is this. A is my area vector. Area vector perpendicular to surface. Please understand, A is the area vector which is perpendicular to surface. Clear? So its value will be given by what? BA cos theta, and you can also write it as B cos theta, say multiplied with A. Why I have written it like this, we'll understand. B cos theta multiplied by A. No need to explain you what is B. B is the magnetic field. Magnetic field. And in this case, when you are using this formula, the magnetic field is taken to be uniform. Theta is equal to angle between B and A. Now children, put your common sense. Okay. Now just see. Suppose my rain is coming in this direction. Look, Zoe, rain is coming in this direction and this is my surface. Rain is coming in this direction and I have kept my surface like this. Will I be able to capture rain? Rain is coming from left to right and I have kept it like this. Will I be able to capture rain? Hey, the rain is coming from left to right and I have kept it horizontal. Will I be able to capture rain? No, not at all. My screen doesn't get affected. What is the area vector now? Facing you. And what is the magnetic field vector? Facing left or right. How much is the angle? 90 degree. Cos 90 is 0. So flux becomes 0. Hang on. And now look, I turn my screen towards me. Where is the area vector? Towards the left or towards the right, whatever. Agreed? How is the magnetic field? Parallel. Angle between them is 0. Flux is maximum. And then we can have intermediate, 60 degree, 30 degree, whatever it is. I hope you have understood what I'm trying to say. Like this, there is no flux. Like this, maximum flux. These are intermediate. So can we write here, if theta is equal to 0 degree, then cos 0 is equal to 1. Phi b is max. If theta is equal to 90 degree, cos 90 is equal to 0, phi b is equal to minimum. And then we can have some intermediates also. Intermediate. And what is the intermediate? Something like, say, theta is equal to 60 degree, then cos 60's value is how much? Half. So phi b is equal to half the max value. Yes or no? Right? Now you yourself think, suppose your vectors are like this. Let's say this is my vector B, and this is what, beta? This is A vector, this is theta. All right. And if I go by trigonometry and I plot this out here, then what is this much? This is B cos theta. B cos theta is the component of the magnetic field along A vector. Listen. Don't get confused. B cos theta is the component of the magnetic field along A vector. That means if your A vector is like this and B cos theta is like this, then there won't be any rain. And how you're getting rain? How are you capturing rain? In that case, area vector points towards you and B is on this side. No. Area vector should point towards you and B vector should also be the same. So that's why between B cos theta and A there is 0 degree. If it is 90, it will not do. So if it is an oblique angle like 0, only B cos theta. See, now you can ask a question, sir, why does in an intermediate portion the flux decrease? Obviously, B was this big, but when you use B cos theta, it becomes smaller. No? Smaller into that, so the wet product becomes smaller. Okay, let's wait and notice unit. The unit is Weber. WEBER denoted by WB. The unit is Weber and it is denoted by WB. That is all in terms of magnetic flux. And if the magnetic flux is not, if B is not uniform, this is just for your understanding. I'm writing here, if B is not uniform, like in work and all, if force is not uniform, then A will be split into many small dAs, and you have to do integral of B dot dA. And in statistics, this can be also written as sigma I equal to 1 to n, all the BIs dot all the delta AIs. Means take one small a, find its B dot A, B dot A, B dot A, and then integrate it. I think we have time, we won't have time for. Done. This brings to our next section. I don't know how much time we'll have, but you can write the heading, Faraday's law of induction. Now comes to Faraday's law of EMI, electromagnetic induction. You can write down the law. So Faraday states, when magnetic flux, now you understood flux. So every case, whether you move the magnet, you move the coil, or you turned on, you did not change the relative, you changed the magnetic flux. So when the magnetic flux linked with a circuit changes, write down, when magnetic flux linked with a circuit changes, when magnetic flux linked with a circuit changes and EMF is induced in the circuit, and EMF is induced in the circuit, right? So you can recall your experiments. In your first experiment, we recall our experiments, okay? Recall experiments. The first one was moving magnet. The first one was moving magnet. So in right below you write, moving magnet means straight away phi B changes. Now we will see that phi B was the fellow who changed in every occasion. Our next experiment was moving coil. Moving coil. In moving coil also, we will say B changes, phi B changes. Here also we can write B changes. Our third one was key turned on. Current builds, B builds, phi B changes. Then key off, current dies, B dies, phi B changes. E steady, phi B steady. So common conclusion, the common conclusion that you have in all these is, here also the phi B changed, here also it changed, here also it changed, here also it changed. So you can write down magnetic flux changes and is responsible for the induced EMF. Magnetic flux changes and is responsible for induced EMF. You can finish this part. Come. And there he mathematically gave E is equal to negative d phi by d phi b by dt. Right. One thing that we will bring up here, generalization. If n coils are there or n turns, then phi b becomes how much? N phi b. Phi b becomes n phi b. Phi b is through one coil. So Faraday's law will now change as E is equal to negative n d phi b by dt. You can write down negative n d phi b by dt. So if I ask you, how can you vary EMF from this expression? Can you tell me? By changing flux, right? So your main motive will be you should vary phi b, but your question is how? So it is EA cos theta. Sorry, BA cos theta. Either change B or change A. How do you change B? Now some examples. B. Okay, we have examples like something, you know, in a bicycle we have something called dynamo. You all have not seen. In our childhood we used to have cycles will have lights. They don't run with battery. So there will be an apparatus called dynamo. You press it, it gets connected to your wheel. As you pedal, keep on pedaling, due to friction, it will keep on rotating the dynamo. In a dynamo, magnet rotates. Magnet rotates and coil is stationary. Has the flux changed? Magnet rotates, coil is stationary. Has the flux changed? Yes. Dynamo used to light up my cycle in childhood. Generator. Coil rotates. Coil rotates. Magnet is stationary. Will it change the magnetic flux? Yes. Generator gives me current. And the best is wireless charging. Wireless charging. The most important one. Wireless charging. So what do you want for charging? You need to give a current to your phone. How are you giving it? You have a wireless docking station. In that wireless docking station, it will change the current, change the magnetic flux related to the coil, and then there is a coil inside in the phone. That's why. So the magnetic flux linked with this coil changes inside the phone. So the phone coil starts generating electricity, and that electricity used to charge the phone. Did you understand? Docking station has a coil, and then when you are a pulsating circuit will start putting an alternating current in it. It will keep on changing. So the magnetic field will change with this. This is docked to another phone. So the phone's magnetic field is also changing now. So the phone's coil is now generating a current which is actually charging. Okay? So I think we are done. So if you change area, you can change the flux. If you change magnetic field, you can change the flux. If you change the angle, you can do. And some examples are dynamo, generator, and wireless charging. In a dynamo, what we do? We turn the magnet. Coil is stationary. In a generator, we rotate the coil and phi changes. Wireless charging, the current in the coil. Which coil? Docking station, the current keeps changing. Magnetic field keeps changing. How the current keeps changing? They create an alternating current. Magnetic field changes. That magnetic field is changing the magnetic field. There is a coil inside my phone also. Right? So it's very simple. In my hand, this is my docking station. There's a current. We always charge the docking station. The docking station will change, keep on changing the current out here. As the current changes, the magnetic field is changing. Then this is docked. The magnetic field of this particular phone's coil is also changing. So inside the coil, current is generated. That is what the current you actually push here. Okay? So I think we're done. We'll meet in our next class.